So what I wanted to tell you a little bit about today is the dark, is about what we know or don't know, because we don't know anything, basically, about the dark side of the universe and what keeps us awake at night, not only because some of us are optical astronomers and do observe at night, but even Steve and I are not optical astronomers. He works with radio, he can observe during the day, and I'm working underground, and we don't know whether it's day or night. So, but there are really fundamental questions that I wanted to address, and I would like this to be as interactive as possible. So if you don't understand what I am saying, or if I am too technical, please raise your hand, and don't hesitate to interrupt. So the first thing that I would like to tell you is, why do we think that most of the universe is dark? That is, it's made of, the ordinary matter is something like 4% of the universe. So what we are made of is only 4% of the stuff in the universe. And there is about 25% of dark matter and 70% of what we call dark energy. And so I will try to get you through the arguments that we have, why 96% of the universe is dark. And then I'll briefly give you some ideas about are we trying to decipher the nature of this dark matter and this dark energy. Because essentially we don't know what either of these two components are. Okay? So for dark matter, I will speak about something which is called WIMPs, weakly interactive massive particles. They were machos in the past, but they have disappeared. And then how we can study gravity with dark energy. Okay, so the standard model, that's basically the energy budget of the universe. You know, of course, that mass and energy are the same thing in general, in relativity. And so we don't make the distinction. You see what is happening there. 4% of atom, 22% of dark matter, 74% of dark energy. And we don't know what it is. Okay. So let's start by asking ourselves, how much stuff is there in the universe? Okay, because I gave you the pie chart and division, but okay, how much stuff there is? And there we have a pretty good idea, because we still believe in general relativity. I'll come back to that a little later in the conclusion. And general relativity is a generalization of Newton's theory of gravity. Okay, and it has problems of its own, because it is not we cannot quantize general relativity, or we can do that in string theories in 11 dimensions. But we don't need to worry too much about that today. The thing which, on the other hand, which is important for what we are discussing, is that the curvature of the space around us is linked to the energy density and to whether the space itself is finite or infinite. And so you can say, what do you mean by, you can ask, what do you mean by the curvature of space? Because we cannot look from the outside. We cannot see whether the thing is curved or not from outside. So actually, since Riemann, who was a mathematician in the late 19th century, we know actually how to characterize the curvature of a space because basically you can do that with what we call geodesics, the shortest path from one point to the next, to the other, in the space that we are considering. So in our ordinary three-dimensional space, which is flat, you know very well that the shortest path from point A to point B is a straight line between point A and point B. Okay? But if you are not Euclidean, if you are not flat, okay, the straightest path will not be a straight line. Okay. So, and the geodesics, what we call this, I should probably turn my phone off. The space, the geodesics will be curved. So, for instance, the flat space, I already said that if you take a sphere, for instance, the Earth, you know very well that the shortest path from here by plane to Paris is not to go, well, we cannot go straight first, and it's not to go at a constant latitude and go up at a constant longitude. It's a great circle, which actually goes fairly close to the pole. That's why when you are flying, you are to Europe, you are flying close to the pole. Okay, so that's what these great circles are, geodesics in a sphere. And these geodesics tend to converge. Consider, for instance, two meridians. Okay, they meet at the pole, and they meet again at the other pole. Okay, so although they are parallel at the equator, they meet. So Euclid lemma or postulate that two parallels never meet is wrong. And that's a characteristic of the fact that the space is curved. And and the geodesics tend to converge. And then there is a negative curvature case where the geodesics diverge. Okay? So in terms of the universe, you can show in general relativity that if the space is flat, the energy density has a certain value, what we call the critical density. And we will measure the density of space as a function of the universe in terms of this critical density. Okay? And we will call this quantity omega, which is the ratio of the density to the critical density. So if the density is equal to the critical density, omega is equal to 1. And you can show in general relativity that we have an infinite universe. Okay. If the energy density is greater than critical density, omega is greater than 1 by definition, and you have a finite universe. One way of thinking about it is that there is enough mass or energy in the universe so it warps onto itself. And basically, it's finite. And if the energy density is smaller, critical density, omega is smaller than 1, we have a negative curvature universe, which is infinite. Okay? So how can we measure the universe geometry? So it turns out that we can see radiation coming from the early universe, from the primordial plasma, what we call the cosmic microwave background. We can see this, and we can see oscillations in this primordial plasma, and we can compute the physical wavelength of this oscillation. We know the distance, okay? And so we can look, what is the angle there subtending the, say, a wavelength of this plasma oscillation. Okay, this is the case where we are flat, where the geodesics are straight lines. Okay. Now, if we are positive curvature, instead of the black geodesics, you will have the red geodesics. And the angle, the apparent angle of these oscillations on the sky will be greater. And if the space was curved the other way, negative curvature, it will be like the green geodesics there, and the angle will appear smaller. And we were able, yes? No, not at all. If it does, it's not, I did not want it to change. No, I don't think. No, you are measuring, say, between two maxima. Okay. Okay, so we have been able to do this measurement about 10 years ago with the microwave background. This was a telescope, the Boomerang telescope, and we were collaborating. Berkeley was collaborating with this experiment. This is which was launched on a balloon at the South Pole, or more exactly at the McMurdo station. The balloon goes, there are winds which go around the South Pole, and the balloon was launched, circulated for about 2 weeks, and came back to the same point, and we dropped the balloon, we dropped the telescope. And we observed the microwave background. Of course, the fluctuations, the oscillation of the plasma are somewhat more complex than just one wavelength. There are lots of spots and so on. But there is, you see, there is a typical size, and that's what we use. If we are flat, that's what we will predict. And you see roughly the same side. If we were a positive curvature, the angle is bigger, and the blobs will look larger. And vice versa, if the angles, if we have negative curvature, like on a saddle of a saddle, then the typical size will look smaller. And the angular size implies that we see implies that the geodesics are straight, that the universe is spatially flat. We have a better measurement now with the WMAP satellite, and we get omega just 1.02 plus or minus 0.02. It should be 0.02. I'm sorry. So it is actually very flat. Okay, so now we know how much matter there is, how much energy there is in the universe, the critical energy density. Okay, we have to try to understand how do we divide the pie. So we can try to, well, of course, we know that there is ordinary matter because we are made of it. Okay, and we can weigh stars. But that's not very much compared to this critical density. Less than 1%. Okay, so there is something which is missing there. So we can try to weigh galaxies. And so what we do, the way we do it is to measure rotation curves. We are measuring with Doppler shift the velocity of objects going around the galaxy. If they are going around the galaxy, yes?
Sorry to take you back, but there's something I'm still not understanding about. You're essentially talking about the mass, the amount of mass in the universe, and you talked about the critical density, but density only tells you one parameter. How do you get scale? How do you know?
No, the space is infinite. So if it's flat, it's infinite. So the total mass will be infinite. But it's a well-defined quantity to take the mass and divide in a certain volume and divide by the volume. And that's what we call the density. Okay. Yes?
If the microwave background is the same in all directions, how can you say it's flat?
It is not exactly the same in all directions. It is the same to within 1 part in a million. But if we look closer, there are fluctuations at the 1 part in a million. And we can look at the typical size on the sky of this, and that's of these fluctuations, and that's what Boomerang did. Other questions? Yes.
I heard that when measuring the North Pole and the South Pole of the universe, you get different regions of the universe. I don't know if this has any play in determining these factors.
No, so we we have the problem that, okay, especially if we do the optical observation, we have the galaxy in the way. So we tend to look up or down at what we call the galactic North Pole or the galactic South Pole. As far as we know, they are, on average, they look essentially the same. We don't see difference between the north, the part of which is above the galaxy and the part which is below the galaxy. Okay. So anyway, coming back to weighing the galaxies, so we can look at clouds. For instance, we can observe in the radio in 21 centimeter, or we can look that they emit, some of the clouds emit also a little bit of light, okay? And we can measure by Doppler shift their velocities. If these objects are bound to the galaxy, we have to balance somehow the centrifugal force that they are experiencing with a centripetal force, which is, we believe, gravity. And if you compute the amount of mass that you need, it's much more than the mass of the star. Okay, and actually there is even something more interesting. So for instance, this is a galaxy M33, and we are looking at a function of the radius, and the velocity that we measure is something like that. And it keeps increasing or is flat. It does not decrease as if there was just mass in the center of the galaxy. The mass does increase, even though, as a radius, even though we do not see stars anymore. The mass increases even though we don't see stars. So there is something else than stars in the galaxy. Okay? And if you try to measure that, we have at least 2% of dark matter compared to the critical density. So I want just to acknowledge two major astronomers there who are actually responsible for a lot of this work. There are Rubin, who is at Carnegie, and Sandy Faber, who is a professor at Santa Cruz. Sandy is about my age, and we are good friends, but they are responsible for a lot of this work, and very nice people. Now, there is another person there, Chris Vicky, who is dead, but was a brilliant astronomer, but was not so nice. He was saying that he was calling his colleagues spherical bastards. And why spherical? Because whatever angle you look at them, they are always bastards. So anyway, what he was measuring the Coma cluster, which is an ensemble of galaxies, about 800 of them, and in a relatively small part of space, and he was measuring their velocity. And that's the plot of velocity as a function of radius. The mean velocity is something like 7,000 kilometers per second. It's just because of the Hubble expansion. But there is a big dispersion in the velocities of individual galaxies. And it says that these random velocities are too large for these things to bind together unless there is dark matter. And he made this observation in 1933. Nobody believed him till the mid-70s. Okay. But it's by far the oldest observation. So this is the coma clusters. We can also see, so these are galaxies. We can see also superimposed X-ray emission because there is gas which is very hot. And the mass is so big that you can actually see the deflection of the light by the mass in the clusters. This is a very massive galactic clusters. And you see in blue, okay, the objects which are blue are galaxies which are in the background. And in particular, there is one object which appears 5 times, there, and there, which is a galaxy which is in the back, and which has been magnified by the lens of the given by the mass of the cluster. There. Anyway, the short story there is that the amount of dark matter that you get from the gravitational lensing, or from the X-rays, or from the dispersion velocities is roughly the same. So we are pretty sure that these things are much more massive than the stars. Okay, so when you do that, you get about 25% when you try to measure the mass of the cluster. Okay? Now, let's go back to gravity. Gravity dominates totally astronomy. And that's what we do. And because dark matter dominates gravity, everything is built out of dark matter. And we believe that we would not be able to form galaxies if there were not dark matter around. Okay? And so, and basically, gravity is just an attraction. That's the only, I have 2 equations in my talk. Acceleration goes as to the mass density, and 1 over the distance squared. And that's what and this is actually interesting because it is unstable. If you have a little bit more density somewhere, it will attract stuff from around it. And the density fluctuations will go and go and go, and finally form galaxies. Yes? There is no speed of light at this level. This is a Newtonian gravity. So, yes, so there is no, okay, I will give you, that's the second equation, I will give you the equivalent equation in general relativity. So there is no speed of light, there is no time of propagation of, and just say that acceleration is the Newtonian gravity divided by Newton constant divided by r squared. And that's just the mass of the object, which is, yeah, essentially nobody believes the CERN experiment, but well, we are checking.
Come back next month.
No, it takes a few years. Okay, so anyway, gravity is unstable, and that's how we form galaxies. And I don't have the time to get through that, but you are forming also tend to put the ordinary matter in the center of the galaxies, and that's what they form stars and disks of galaxies, and a halo of dark matter around it. Okay. So basically, that's what we can simulate, and this looks pretty much what we observe. There are small details, that there are much too many dots, small satellites there that we don't observe that many, but more or less we can reproduce what is going on. Okay, there are other astrophysical evidence which gives us omega of the order of 0.3 for the growth of structure. Microwave background, these fluctuations that I was speaking of, we can measure them, and they are sensitive to the amount, the vibrations of the plasma is sensitive to the amount of matter, and we can get the total matter density of 27% roughly. So we are pretty sure that there is dark matter. Now, we are also pretty sure that it is not ordinary matter, because we can measure the matter, ordinary matter, very well in two different methods with two different physics input, and we get the same result. And that's another big accomplishment of the last 10 years. So for some time, we had known that the baryon density, baryons are protons and neutrons. Okay, they are ordinary matter. The electrons are coming with them. Okay. It can be measured by the primordial abundance of light elements, like nuclei. Okay, helium, deuterium, helium-3, lithium. These things are produced in the Big Bang, and we can measure them. And we are roughly very consistent measurement between all these abundances, and this points to a particular value of omega, which is of the order of 4%. Totally different. The oscillations of our primordial plasma with the cosmic microwave background also gives us some idea of the density of the baryons. And so you see, these are the power spectrum. We analyze in frequency, basically, what we see on the sky. Okay, and this beautiful power, what we call a power spectrum, a little bit like if you were analyzing the noise, the frequency of a sound. That's exactly the same idea. And the relative height of these peaks are sensitive to the amount of baryons. And sorry, they were supposed to tell. Okay, I don't know what. The net result. This also gives 4% of the critical density. Totally different physics, totally different systematics. This is quite amazing that we get the same result. And it's 4% to with a 10% of better accuracy. Okay. We also know, so it's not ordinary, dark matter is not ordinary matter. It's very difficult to. We also know that it is does not follow light. Okay, so let me. I don't know how I can start this thing again. So what we observe is the blood cluster, which has the blue is where the mass is. We can measure that with gravitational lensing, the same method I told you before. And the gas we can measure with X-rays, and it's in red. That's where the gas is. It's not at the same place. And what we believe this object is, and so I'll sorry, is two clusters merging or going through each other. And the dark matter keeps going because it does not interact. And the galaxies keep going because they're compact. And the gas, which is between the two galaxies, shocks with itself. The mass of gas shocks, get hot, and that's what we see here. Okay. But we are still missing. So we have dark matter, something like 25% plus, yes?
So that interaction with matter and dark matter was strictly gravitational.
That's gravitational. The gas is not gravitational, it's electromagnetic. Okay. That's electromagnetic. That the two masses of intergalactic gas in the clusters are really colliding and form and become hot. And that's what we see in X-ray. But the dark matter does not interact with itself, or, or at least not very strongly. Otherwise, it will not behave as dark matter. But we are still missing 70%. Okay, omega baryon 4%, omega dark matter. My numbers are always changing a little bit. I should be consistent, but you see that's basically 30%. We are missing 70%. And it has to appear relatively late. This additional component has to appear relatively late because otherwise we cannot form galaxies. And that's what we call dark energy. And how do we see that? It's just by mapping the expansion of the universe. So our problem is that we have to look very far, because we would like to see objects which are very early in the universe and try to see whether the expansion at that time is the same as now, or more exactly how we expect it. It should be a little faster, we know, because there is stuff in the universe, but okay, whether it behaves according to expectation. So the objects that we are using are supernovae. These are supernovae observed close to galaxies, and you see that the supernova is as bright or brighter than the galaxies. So we can see them very far. Okay, and what is also interesting, that this a certain type, which we call type 1a, it doesn't matter what they are, can be standardized. That is, if we look at the light curves, that's time, and that's the amount of light that we observe from these objects. If we correct for the width, for instance, or for the rise time, the fall time, we can put them all on the same plot, and basically we can measure we know the amount of light that the supernovae are emitting to better than 10%, which is quite interesting for astronomers. We don't do many measurements at 10%. Okay? And what do we observe? We observe that if you plot the luminosity, and because we are astronomers, we are always plotting things the wrong way. So no, we are totally historical in nature. So magnitude was fainter, and this back to Babylon, and we have not changed the. So things which are fainter are going that way, and this is the redshift, which tells us how far, basically the time at which light was emitted. Okay, and the brightness tells us how far the object was. And you see that, and these are the two publications in 1998 by Perlmutter and company and Adam Riess and company, showing that actually the luminosity of the supernova type 1a were fainter than we expected, which meant that the universe has accelerated its expansion. They are further away compared to what we expect. They're further away than we would expect. Of course, you know, these names now are familiar, Perlmutter and Adam Riess, and the postdoc who was working with him, Brian Smith, got the Nobel Prize this year for this discovery. So what does this mean? Okay, so that's Einstein playing with bubbles. This means that the universe is accelerating, and that somehow gravity manages to be repulsive. And that's the big thing. And how does it become repulsive? Actually, it can happen in general relativity. These were the expression that we wrote down for Newton. In general relativity now, we have the speed of light appearing now. Okay, so there is this 1/c² there. And then we have the energy density and 3 times the pressure, which appears in the similar expression. So if the pressure is large and negative, okay, this acceleration, instead of being attractive, the force, instead of being attractive, can be repulsive. And that's what we believe is happening there. Oh, that's a volume. That's a volume, yeah. I'm cutting out a volume, and I'm asking what is the force, the gravitational force that this volume is exerting on something.
Okay, so the volume, not the point mass, but
yes, and I have to put, so there's a certain energy density, so that's basically the same term as this one, but there is in addition 3 times the pressure. So if pressure is negative, and we believe actually that the dark energy has a pressure which is equal to minus the energy density, or very close to minus the opposite of the energy density. So this term becomes extremely negative, and actually has flipped and even doubled the, not only flips the gravity, but doubles its strength. 1 minus 3, which is minus 2, and that's doubling the strength. Yes?
So this is all based on the standard candle power, basically, of,
yes.
the supernova. Is there anything else that could explain a diminishment of that?
We have looked for the last 13 years for this kind of things, and no good explanation has been given. And now, but we have another reason why we believe that is that we do know omega equal 1. We know roughly the amount of dark matter and ordinary matter. And we are missing this 70%. Okay, and we know that it appears late. And to appear late, because it has to have negative pressure. So we know from what, without the supernovae, we know something which looks very similar to what the supernovae see. Okay, so that's the current status. Oh, I don't think there have been a recent review. Maybe in the double prize lectures, there will be recent reviews. But its situation has not changed in terms, we are just more accurate. So, actually, I'm coming to your question there. How does this fit together? So we can put omega lambda, that's what we call the density in this dark energy, omega in matter. CMB tells us that we are flat. The supernova tells us, the clusters, sorry, tells us that we have something of the order of 0.3, 0.25, and that's what the supernovae gives. And all the pieces of evidence fit. Totally consistent. This is extremely surprising. That's the most contrived universe we could imagine. So this probably is the parametrization. And that's how we got the pie chart. Okay.
Naive question. Could you give some intuition about negative pressure? What does that mean?
Take a rubber ball and try to expand it. That will give you a negative pressure inside the ball. So it's the opposite.
Balance the pressure inside and out.
Okay, so if you have a gas under positive pressure, it will expand.
Yes.
If you have a rubber ball that you've expanded, now it wants to contract. And that's what the negative pressure is. Yeah, I mean, it's very strange. So general relativity is not as intuitive at all. The pressure is negative, and you would expect the things to contract. But no, the gravity becomes negative, and then it expands. Okay.
I assume the 3 times the pressure comes out of the Einstein field equation.
Yes, yes.
But what's the physical explanation for why it's 3 times the pressure?
The numbers, okay, so can give you a feeling. Obviously, in general relativity, we have to take into account energy and momentum. The energy is the energy density term. The momentum is related to the pressure. The pressure is related to, okay, if you have particles bouncing on in the gas bouncing on the wall, the force is really related to the momentum of the particles bouncing on the wall. So, and the number 3 comes from the fact that you have 3 dimensions. Yes?
You didn't mention black holes. Do they enter at all into the consideration?
Yes, they do, and I wanted to simplify it a little bit. So, in principle, they will not count as baryonic because, in principle, a black hole has forgotten where it's coming from. But we know that if the black holes were formed recently, they would have been probably formed out of baryons. And then they are covered by the arguments on the number of baryons that I gave. Now, if black holes were formed in the very early universe, much earlier, then this doesn't apply. Now, we have looked for black holes of the order of a solar mass or in our galaxies, and these are the matches that I was mentioning before, and we have not seen them. And there are arguments. Okay, we can cover actually a very large region of the mass of black holes where basically they don't appear to be the dark matter. Okay, so we have a number of questions. Why omega baryon is of the same order of magnitude as omega matter, omega lambda? And I did not speak about neutrinos, but they are a little less than that. But why does the dark energy appears now, or the last billion years, or 2 billion years? Okay. What is the nature of dark matter, and what is the nature of dark energy? Okay, so I should stop relatively soon. 10 minutes. Okay. So let me give you an idea about at least of the dark matter aspects. What is happening there. So you can make a map of possibilities, and I don't want to enter. There are many possibilities. I would like to focus on one possibility just to give you an idea. This WIMPs, weakly interactive massive particle. And one way is this very special class of candidates, and I try to summarize the basic idea there without any equation. Both particle physicists and cosmologists are looking for a missing piece in the puzzle. And basically, a good comparison is to say that they believe that the piece which is missing has roughly the same shape. So probably it's the same piece which is missing. So the cosmologists say, if dark matter is made of massive particles, which were in equilibrium with the rest of the universe at early times, they should interact roughly at the interaction strength of neutrinos. And they are not neutrinos, we believe. They are massive, very massive. Particle physicist says, oh, our standard model is unstable. Even if they discover the eggs, or they have discovered the eggs, okay, the evidence is not yet compelling. There is a problem, is the mass of the Higgs will go to infinity. And the mass of the W and Z will go to infinity. And okay, there are lots of things which happen, which are bad. In order to stabilize, we need something like supersymmetry or some new physics at what the particle physicists call the TeV scale, tera electron volt scale, which naturally contains stable, which will stabilize the theory. And this will naturally contain stable particles, which interaction strengths, which are roughly the interaction strength of the neutrinos. Okay, so the cosmologist wants particle with interaction strength of the neutrinos. The particle physicist wants to stabilize their model, and what they are led to is probably particles which have got the same properties. So it may be just coincidence, or it could be that a powerful hint that we are that's the solution. And that's what we call weakly interactive massive particles. So there are three complementary approaches. So the dark halo of our galaxy is full of these WIMPs, if they exist. So you can try to detect that on the Earth, because the WIMPs, the Earth is in the halo of our galaxies. The WIMPs will go through the Earth without any problem. And actually we go, and that's what I do, we go underground to protect ourselves from as much stuff as possible. And we are looking for the small scattering of these WIMPs on very sensitive targets. Okay. You could try to look for the WIMPs annihilating with each other in the cosmos, and that's what gamma rays and neutrino detectors are trying to do. So that's the Fermi glass satellite. These are Veritas in Arizona. Or you can try to produce these WIMPs at the Large Hadron Collider. And we are living in this very interesting time where all three methods are roughly the same amount of sensitivity. Now, you know already that we have not observed anything because you would know about it. But anyway, there is these are the WIMPs, obviously. Nothing against the Romans. And but I have much in favor of the Gauls. And, oh, this is misplaced. What I wanted to say is that we have actually a very large expanding community. We are more than 500 physicists worldwide now looking for this dark matter by direct detection. We were 0 25 years ago. Okay, so my mother, before she passed away, and I was one of the first few, my mother, before she passed away, told me, I did not know that you were that persistent. I've never seen you doing the same thing for 25 years. So that's what we do. We have detectors which are kind of, okay, let me finish and I will, 7.5 millimeters, 75 millimeters, 3 inches diameter, about 1 inch thick. Okay, and we are trying to look for interactions of the WIMPs into these guys. These guys are at very low temperature. It's not this temperature, which is just that the temperature at the surface. The mine in which we are is in northern Minnesota, and it's the coldest place in the United States, actually. And this is a picture taken Memorial Day. It was a cold Memorial Day. And these are, but these detectors are operated at very low temperature, 50 thousandths of a degree Kelvin. 50 thousandths of a degree above absolute zero. And we have to make, okay, so that's what we do. We have to be careful about radioactivity. We are, okay, that we are just installing a set of detectors and so on. So, yes?
So you call what is weak
So they interact with themselves and produce ordinary matter, okay? Or they can scatter. They can scatter unordinary matter. Okay, so it's somewhat model dependent, but we have actually something which is normalizing everything. Is that in order for them to have the density today that they have to have a certain interaction strength, which is a weak interaction. And that kind of roughly normalizes the thing. Okay, let me go rapidly the general situation. So we have limits, basically. So this, we put the cross sections of WIMP nucleon versus the WIMP mass, and basically everything which is above this curve is excluded. Excluded. Yeah. Except, and that's my next point, except that you see these blobs, these things, and these guys have said that they observe something. Okay. No, okay, so far no signal either from the LHC and the Fermi. Except that if you look at this, listen to this guy, says we have observed WIMPs. Actually, in the low mass region in particular, there is this, another experiment which says that. So they say all they observe, they say that they observe something. Dama is the most famous one with a modulation of the signal of the last 12 years. The only problem is they don't observe the same thing. And the other problem is that they are incompatible with much more sensitive experiments, including ours. I think we are practically solid counter evidence. Yes? Except that the sun wave is summer winter. And just the weather on the
For testing, for theoretical, or for
no,
experimental.
Yes, experimental. So we do observe also, we do expect a modulation if there is a WIMP signal, because the Earth is rotating around the sun. It turns out that it's also lined up with summer and winter. But the muons, the cosmic muons, are also modulated roughly the same way. Okay, so that's the subtle effects which are difficult. Okay, so it's a very lively discussion. And these guys are, I think, in trouble. Okay, so okay. Now, of course, we eventually come back and we'll have a big meal together. Actually, we do speak quite a bit about getting united. We have a common roadmap where here we are, this is the cross-section versus mass. And we are a little bold, but we are thinking of doing about a gain of a factor 1,000 in sensitivity in the coming 10 years. I don't have the time to speak about dark energy. Let me conclude. Can always ask me questions. So I think we have a fascinating time in cosmology at the moment. Extraordinary progress with CMBR, large-scale structure, but we have profound mystery about this dark side. What is it? And the model that we have is totally unnatural. And actually, some people, including me, have been worried about this comparison with epicycles in the Greek astronomy, where, as you remember, Ptolemy, 100 AD roughly, had a very good description of the planets orbiting around the Earth. And because the observations were not were too good, they had to have the planets orbiting on circles rolling on circles, because circles were the perfect shape. That was the theoretical argument. The only problem is that, of course, everything was centered around the Earth instead of being centered around the Sun. Are we making the same kind of mistake? Every time that we measure something in cosmology, we have to introduce something new. Okay. So we have really two scientific priorities: to detect dark matter and to better constrain the nature of dark energy. Okay. For dark energy, I think, for me at least, and many colleagues, it has, unless it's totally random and the universe has been selected to have a particular value of the dark energy, which I don't believe a minute, it's probably, we are touching something very fundamental about the quantum properties of gravity. So, thank you.
That could these supersymmetric particles that haven't been detected, could they be the dark matter?
Yeah, the supersymmetric particles are actually one of the primary candidates for these WIMPs. So the lightest of the supersymmetric particles will be stable and would be the dark matter. Now, the Higgs does not necessarily imply dark matter, supersymmetry. The Higgs is a way for us to be able to introduce mass in our theories in a very elegant way in which our equations are not diverging. If you put mass by hand, you have infinities cropping all over the place. If you put it with the Higgs mechanism, everything behaves. Okay. But the problem is that once you do that, if you look at the next order corrections, the corrections will add up and the mass of the Higgs will go to infinity, dragging the mass of all the particles with it. So we know that's not the case. Okay, so something else has to happen. It could be supersymmetry, it could be some kind of global symmetry, it could be large additional dimensions. That's just the fad in the theoretical community. But what we are pretty convinced that something else has to happen, and that's why the Large Hadron Collider is very important. It's important for the Higgs, but it's also important to see what is stabilizing the model. Now, there is tension. The most naive ways of supersymmetry are basically excluded by the current results of the LHC. So there is about a workshop every week where we are scratching our heads and saying, okay, some people like the older, like me, the older members of the community says, don't worry, it's not, I'm quoting Steve Weinberg there, it's not a law of nature that theorists have to be right. And it could be something else. Yes.
I was just wondering, other than for the purposes of answering the mysteries of what is taking up all that other area, are there any figuring out what dark matter and dark energy are specifically? Are there any kind of tangible, real-world applications or impacts that it would have in terms of things that we're trying to, I guess, advancing life, other than being theoretical and answering that theoretical question? Are there other applications that knowledge would?
you are asking me to be very visionary. When the condensed matter physicists were dealing with germanium and properties of electrons in germanium, this would look pretty esoteric. Okay, we have a whole civilization based. Germanium was too difficult to use, so we use silicon. But we have a whole civilization based on silicon. Okay, so it's always very difficult. Another example, also at Bell Labs, by the way, Charlie Towns, and he was a young physicist, was called in by his boss and said, Charlie, you have to do something else. I don't see how this kind of molecular spectroscopy has anything to do with telecommunication. Charlie Towns was inventing the laser, which is very simple. So it's very difficult to guess where things are going. This being said, dark energy is only seen at very large distances, so I don't know exactly what you can do, but with it, I'm sure that there will be science fiction trying to master dark energy to go, science fiction novels to try to master dark energy to go very far. I have no idea. I have no idea. But on the other hand, let me go back to the philosophy. The philosophy is actually interesting. Not only we are not at the center of the universe, we know that for a long time, but we are not even made of the stuff the universe is made of. So in some senses, that's the ultimate Copernican revolution. Yeah.
Maybe say again why dark matter should be invisible in the electromagnetic radiation.
But that's what we see. Well, more exactly, that's what we don't see. We see the dark matter through its gravitational effect. We don't see any interactions with electromagnetic waves. The only interactions that we see is the gravitational interactions. It deflects light, but we don't see it. And we can put limits on the interaction rate with ordinary matter and with electromagnetism.
The limits are more sensitive from your direct detection experiments.
Yeah, but there are other limits which are related to, for instance, the bullet cluster or interactions. We can also put limits of the dark matter with itself. Yeah.
Dark matter, because of the pie chart, we have atoms that there's atoms here in the room. We're made of atoms. Is dark matter also
in the room? Yeah, to give you an order of magnitude, if it's indeed made of WIMPs with, say, typical mass 100 times the mass of the proton, there are billions of those particles going through each of us every second. Fewer than neutrinos from the sun, but quite a bit. So the problem is that we have to try to detect them. Their interaction rates are so small that it takes a lot of precaution. The current limits that we have are about 3 interactions per kilogram of target per year. Per year.
So you're actually quite a good whip detector.
But wait, each of us.
100 detections per year.
Yeah, but okay, they deposit very little energy, which is totally masked by, and that's why we are using low temperature techniques, because to be extremely sensitive, basically. Yes.
You said something that was really beautiful just a minute ago. I didn't quite understand why. Is that we are not even made of the stuff the universe is made of.
So the baryons, the ordinary matter of which we are made of, is only 4% of the stuff in the universe.
And then I guess the other part is, I'm just curious if you have
Oh, okay, so I have to speak about that. Okay. I should have brought a slide. So, essentially, none of us, including the authors, are really believing that's really the case. The technical problem is that, okay, so we are sending neutrinos for about 700 kilometers between Geneva and Rome, basically. They arrive 20 nanoseconds. They appear to arrive 20 nanoseconds, 20 billionths of a second earlier than we expect. And so we know the distance pretty well. We know that the time, we can synchronize our clocks pretty well because we use GPS. And so there should not be any problem with that. On the other hand, the particle, the pulse length of the neutrinos is, if I remember well, 16 microseconds. It's 1,000 times larger. So how do you detect either the average position of the pulse or the edge of the pulse without systematics in one part in 1,000? So that's the problem. That's the problem. And so there are many proposals of saying your pulse is, instead of being square or rectangular, okay, constant for a given time, is a little tilted one way, tilted the other way. And that can basically change the average.
One more question. Okay, if there are no more questions, let's thank the professor.
You know, of course, that mass and energy are the same thing in general, in relativity. And so we don't make the distinction. You see what is happening there. 4% of atom, 22% of dark matter, 74% of dark energy. And we don't know what it is. Okay. So let's start by asking ourselves, how much stuff is there in the universe? Okay, because I gave you the pie chart and division, but okay, how much stuff there is? And there we have a pretty good idea because we still believe in general relativity. I'll come back to that a little later in the conclusion. And general relativity is a generalization of Newton's theory of gravity. Okay, and it has problems of its own because it is not we cannot quantize general relativity, or we can do that in string theories in the level. So in our ordinary three-dimensional space, which is flat, you know very well that the shortest path from point A to point B is a straight line between point A and point B. Okay? But if you are not Euclidean, if you are not flat, okay, the straightest path will not be a straight line. Okay. So, and the geodesics, what we call this, I should probably turn my phone off. The geodesics will be curved. So, for instance, the flat space, I already said that if you take a sphere, for instance, the Earth, you know very well that the shortest path from here by plane to Paris is not to go well, we cannot go straight first. And and it's not to go at the corner. So what I wanted to tell you a little bit about today is the dark. Is about what we know or don't know, because we don't know anything basically about the dark side of the universe and what keeps us awake at night. Not only because some of us are optical astronomers and do observe at night, but even Steve and I are not optical astronomers. He works with radio, he can observe during the day, and I'm working underground, and we don't know whether it's day or night. So, but there are really fundamental questions that I wanted to address, and I would like this to be as interactive as possible. So if you don't understand what I am saying, or if I am too technical, please raise your hand, and don't hesitate to interrupt. So the first thing that I would like to tell you is, why do we think that most of the universe is dark? That is, it's made of, the ordinary matter is something like 4% of the universe. So what we are made of is only 4% of the stuff in the universe. And there is about 25% of dark matter and 70% of what we call dark energy. And so I will try to get you through the arguments that we have, why 96% of the universe is dark. And then I'll briefly give you some ideas about are we trying to decipher the nature of this dark matter and this dark energy. Because essentially, we don't know what either of these two components are. Okay? So for dark matter, I will speak about something which is called WIMPs, weakly interactive massive particles. They were machos in the past, but they have disappeared. And then how we can study gravity with dark energy. Okay, so the standard model, that's basically the energy budget of the universe. You have 11 dimensions, but we don't need to borrow too much about that today. The thing which, on the other hand, which is important for what we are discussing is that the curvature of the space around us is linked to the energy density and to whether the space itself is finite or infinite. And so you can say, what do you mean by, you can ask, what do you mean by the curvature of space? Because we cannot look from the outside. We cannot see whether the thing is curved or not from outside. So actually, since Riemann, who was a mathematician in the late 19th century, we know actually how to characterize the curvature of a space. Because basically, you can do that with what we call geodesics, the shortest path from one point to the next, to the other, in the space that we are considering.